It's about uh, better coloring of three-color graph. My name is Kenichi Kawabayashi, and this joint work is Miki Throw Up and Hirotaka Yoneda. So let me begin with presenting a problem. Input graph is three-color graph, and what you have to do is color this graph as few colors as possible in polynomial time. That's important. So input graph is three-color graph. I guarantee you that it is three-color graph, but I'm not going to tell you how to color. Your task is color this graph as few colors as possible in polynomial time. It turns out that this problem is one of the biggest algorithm problem in theoretical computer science because firstly, two deepest tools in all of theoretical computer science are needed. Namely, for lower bound, we need some unique game conjecture. And upper bound, we need some different programming technique. That's why I'm saying one of the outstanding problems in TCS. And in the future, we will definitely need graph theory approach. And this is what we were going to talk about. Or again, problem is that graph is three-graph graph. So input graph is a three-graph graph. And your task is to color the graph with as few colors as possible in polynomial time algorithm. Um, it turns out that best known algorithm is a combination of graph theory and STP result. Before telling you the result, let me tell you how difficult this problem is. Firstly, graph coloring is hard in general. It's known that you can't really approximate the graph coloring. And it's even hard for three-graph graph. This is because knowing three-colorability doesn't help much. So what can we tell about three-color graph? Yes, certainly this graph doesn't contain a full complete graph of four vertices because that requires four colors. We can also assume that this graph doesn't contain K4 minus, meaning K4 minus 1 edges. Well, this is because if you identify two vertices of degree 2 in K4 minus, that's still a three-color graph because K4 minus, these two vertices need to receive the same color in three-color graph. But we can't really say more about this. That's the problem. These two are important, but we can't really say more about that. So knowing three-color graph doesn't help much. That is a big problem. So let's talk about what is lower bound. Well, it's a typical NP-hard program with three colors. In fact, NP-complete graph is one of the earliest NP-complete graph shown by Gary and Johnson Stockmeyer, 1974, 50 years ago. It turns out that you can't really color with four. You can't really color with four colors or three-color graph. And it's also known that it's unique game assuming you get conjecture, you can't really color with any constant color. But we don't really know the right answer. It might be possible to color graph G with like log n colors in polynomial time. Let's go to the upper bound result. So one was the first result by Abby Wickerson is good n colors are enough. And then the Bloom showed that into the 3/8 is enough. Um, but then, so these two in the colored red actually means it's based on the graph theory, and then blue is based on the SDP. And after the Bloom result, there are four results appearing using SDP result. The first one's Kaga, Motor and Sudan result. These are actually the tools of this result are from the Gumans-Williams SDP result, and the Laura Crumpton-Charika result. This result is from a technique of a Spartan cut by Aurora Lau Basilani. So these four are based on the SDP, and Mikkel and I proved something based on the graph theory. And we actually pinned down to into the 0.19996, below into 0.2 10 years ago. Now here's our main result. Technically speaking, what we proved is the following. We show that if mean degrees at physical now, we can make progress toward n over d2 to the 1/2. Here, make progress means that you can make some reduction, preserving the recoverability. And using this technical result, we got down to into the 0.19747. And this is actually a combination of SDP and graphs. So in order to understand why we need this n over d here, under some degree condition, I'm going to tell you when the SDP helps and when the graph theory helps. So in this table, it's a combination of the SDP and a graph theory, and we finally this result is into the 0.197. So, by the way, the zero hide the log n factor because we don't care. All right. At the beginning, I said that the result is a combination of SDP and graph theory. In order to know why we need both SDP and graph theory, we have a following name, but this is actually due to the Aurora, Kramtak, and Charika statement says the following. Given any n-vertex graph and parameter d, then in polynomial time, you can find the induced subgraph of all that is n over 4 such that either the max degree of this graph is at most 2d, or mean degree of g prime is d over 2. So either the max degree is bounded or mean degree is big. So that's what the theorem says. So if you know this result, then we can tell you about how we combine the SDP and the graph theory. So if mean degree is large, then graph theory would do a good job. We can make a progress toward into the n over d2 to half Caroline by our new result. And if max degree is small, then SDP would do a very good job. Namely, SDP can make progress toward d to the 0.3264 Caroline by kilometer. So that means the max degree is bounded, then the SDP would make a progress with respect to d max degree and d to 0.3264 Caroline. But we can combine the following. So all of these combination of basically you just pick up the one of the coloring from SDP side as blue, or graph theory side that will be red. So from here, here d to the 1/3 or one of these two, and the Lorca, Charika, Crompton, they make a progress. You from here d to the 1/3 to this value, and the Crompton also make a progress with this. Now, um, um, now we make a progress with the um, so from the Mikhail and me actually make a progress from this to the end to the end to the D, and over D to the 4/7, and then over to the 12 over 23rd. And this makes the progress on this paper is from here to here. Okay. Let me just mention our technical contribution in next 5 minutes. So what we can do is we can find the independent set of order NT to the half by graph theory approach. And this can be done by using some graph theory approach, what we call sidecut. In fact, it's a combination of fast-cut. This was previous contribution with Mikkel. And by the way, Bloom can only make progress within the 2/5 times D to 3/5. So this is better than the Bloom. Okay, so let me just define what is a sparse cut and side cut. First, the groups have a nice lemma saying that you can find such a structure, meaning that one vertex of red and the first neighborhood is basically the degree five, and green and blue almost half. And in the second neighborhood, you have blue and red and green, but either a number k. So we want to make a progress on k coloring, k to the n to the n over d half. Um, then what we can say is the following. So firstly, let me define the sparse cut. Sparse cut is here, where it's from x to y, and also the number of edges from x, they're the only neighbors of y. From y, there are only few edges going out. That's why we call sparse. And then we complete the sparse cut here and make progress in this side. So that is what we do with Miko. In this work, however, we make a little bit more. So we first take a sparse cut, and then we find a side cut. This is orange. Side cut means that we have some vertex which has some neighbor here, and the second neighborhood goes like this outside here. And it turns out that this cut, this side cut is sometimes better. In fact, most of the cases it's better because number is from y to x prime in average is bigger than the number is from y to x. And it turns out this makes a difference. And the sparse cut side cut, we get the following. Either we can make a progress toward k coloring, or otherwise, what we get is that the side cut gives us something like a bipolar graph in this, this one, x and y, such that the degree from y to x is still big enough for our purpose. And we actually return in this instead of st. But instead of looking at s and t, we look at x prime and u prime, x prime and y prime, sorry, here. This has some improvement over the previous work with Mikkel. We in our work, in previous work, we don't really introduce light cut. We only deal with the sparse cut. And this has some advantage. We can get some subgraph xy from such that the degree from, again, from y side to x is much higher than that obtained from the sparse cut. This gives us a much longer recursion sound available. Again, so in previous paper, we just recur x here and y here. In current paper, we recur here to here instead of s and t. So the next iteration will be here. And in our previous work, we look at this one. And the difference is, as mentioned here, the degree from y to x is much higher than this. So degree from here to here is much higher than that from here to here. So that makes us some much longer recursion. So in the previous paper, we have only 5 rounds, but here we have almost infinite amount. So this allows to improve from into the 12 over 23 to n over d to the half. Okay, conclusion is that we get some improvement for 3 color graph since the previous work with Mecca. But we know that there are something. For example, SVP gap exists, which means that you can't really combine SVP and graph theory if you really want to go beyond into the for example 0.15. So that tells us that we definitely need a graph theoretical approach. The right value might be like polylog n or even polylog m, but we still miles away. Into the epsilon curve for any that for any epsilon bigger than zero, that would be probably great, but still miles away. All right, thank you very much. Um, okay, so sorry. We have some. Our next target will be like this one for n over 2 half. This will imply the purely graph circle result into 1/3, which beat our previous went to 4/11. And the present paper, in this paper, requires actually this one, but a degree band. And that we couldn't get rid of it from our analysis. All right, thank you very much. Here's a nice throw from cat. My cat is focal simply because cat is brain graph. Thank you very much.